Welcome back, everybody, and welcome to this session where the aim is to continue the discussion which we had last week on Boltzmann machines and generative methods. And then we are going to look into what is called a variational autoencoder. This is not, it sounds like an extension of what we did before with autoencoders, but it's actually quite different from that. But there is a kind of decoder and encoder functionality in it. And we are going to go through some of the mathematics behind the theory for variational autoencoders. Now, variational autoencoders were extremely popular in the last decade, but they have lost, again, some of the, how to say, momentum, which also Boltzmann machine had, compared with the energy-based models where you replace, let's say, a Boltzmann machine with a deep neural network, and also diffusion models. But we will anyway go through variational autoencoders because this is something which many of you may encounter and have been very popular. And we want to expose their strengths and weaknesses. And when you see some of the weaknesses, you understand also why they can be difficult to actually generalize to more complicated cases. And we are going to need, again, things like Bayes' theorem and some of the statistics, which is essential to understand what a variational autoencoder is doing for us. However, I'm going to repeat some of the things which we discussed last week about Boltzmann machines, because many of these ingredients, they enter the discussion of variational autoencoders as well. When we are done with the variational autoencoders, we are going to look at the generative adversarial networks, and we will probably start scratching the surface today or begin with that next week. And that, together with diffusion models, will be the last topic this semester. So the material is something which you find at the usual place. And there are also recommended readings. And we have this textbook by Goodfellow et al., where there's quite a discussion on variational autoencoders, although I have to say it's a little bit superficial. It doesn't give you the whole mathematical aspect of these variational autoencoders and generalized adversarial networks. So the plan today, as I said, is to give you a kind of reminder from last week. So we're going to dive into the whiteboard again, and you will find many of these details as in the Jupyter notebook from last week. And then we will also look at codes for some of these energy-based models, and we will discuss something which is called Langevin sampling. So Langevin sampling is also called stochastic gradients, Langevin dynamics. And it's a much more efficient way to perform the sampling when we are setting up the probability distribution, because it is a sampling which actually samples directly on the log of the probability distribution, and it has much shorter correlation times compared to more traditional methods like Gibbs sampling, which we discussed last week, and also the standard metropolis sampling. So the metropolis sampling requires that you actually can sample from the full probability distribution. And normally the probability distributions which we have, they are multidimensional beasts. And we don't want to sample from a multidimensional function. Gibbs sampling looks only at one of the variable which is suggested change it, and whereas we compute the conditional probability. So I'm going to remind you of some of these statistical concepts and definitions, because they also enter the discussion of variational autoencoders. Any questions so far? So many of the codes which I also link to are codes which I have taken from other sources. And if you go into Keras and PyTorch, you will find tons of examples on how to use energy-based models, you can use variational autoencoders, etc., etc. And normally I would recommend using this software for the kind of analysis which you're setting up. I also realized this morning that they haven't updated project 2. But project 2 is going to, for those of you who are not going to write a long project, project 2 is essentially going to deal with you implementing one of these generative models. That could be Boltzmann machines, or it could be variational autoencoders, generalized adversarial networks. You can use this to study differential equations, or you can use this on, let's say, classification problems or other types of problems. So the kind of data, yeah. So the idea with project 2 is that you actually use generative models. That's the kind of idea. Unless you have enough material from project 1 so that you can keep going with what you did in project 1. So some of you have taken that path. There are people working on physics-informed machine learning, and they're actually just extending that by including things like different types of differential equations. There were people who studied the solution of a Navier-Stokes equation with simplified boundary conditions. And then they've extended this in the second project or the second part to include more complicated boundary conditions. So these are things which it's very much up to you to discuss. But the sketch which I will make is about this generative models. And I actually forgot to upload the proposal. So this is something which I will do after the lecture today. Sorry for that. It's my brain here which is working slowly. Okay, so I'm going to switch back to the whiteboard, and I want to remind you of some of the basic statistics concepts which we used in connection with Boltzmann machines, because many of these are going to migrate into the discussion of variational autoencoders. So one thing with variational autoencoders is that this relies heavily on Bayesian statistics, which again relies heavily on you making a model for some of the conditional probability distributions. And as you will see, one of the standard models is the Gaussian distribution, because with the Gaussian distribution, it's easy to calculate gradients in a gradient optimization. So let's switch over to the whiteboard and remind you of some of the things which we did last time. So one of the basic definition which we have is a probability distribution for some stochastic event x of I. And then we have today we are going to call this latent variables, but in the Boltzmann machines, we call them hidden variables because we define hidden layers. So we have an h of j, and then we have some parameters theta. So later, I'm also going to skip theta just to avoid notational cluttering in the notes here. But theta are the parameters which we are going to optimize. So we're going to take the derivatives with respect to theta. And what we did then was to assume that there was a function f, which depends on the h of j and these parameters theta, divided by a normalization constant, which is normally actually in the literature in machine learning, is called the partition function. This quantity which we have here, just to remind you of the statistics naming, this is called the joint probability. So I hope you don't get offended if I remind you of some of the names of these statistical concepts. And we're assuming now that we can have a model for that. And the quantity which we have here, this partition function, just to remind you of these quantities again, this is now given by an integral over x, where we have not defined the integration domains. And then we have a integral which now involves the joint probability. And note now that here, I'm now assuming that I'm summing over variables x, or integrating over variables x, and that these x's can be discrete or continuous, like in this equation, or if they are discrete, I have some sum over x of I and h of j, and then I have my p of x of I of h of j of theta. And obviously, this quantity here, as we discussed last time, if we have a binary case where x and h take binary values like 0 and 1, we have two types. So if we have a binary case, suppose now that x of I takes only values 0 and 1, which was the example of a binary Boltzmann machine. Sorry, not that one. In that case, if we now have a sum which goes from 1 up to n here, m, and this goes up to n, then we would have 2 times m, 2 to the power of m, and 2 to the power of n possible realizations, or possible configurations, as we call them. So clearly, these sums become, at a certain point, unwieldy, unless we have some very few of these variables. So this is one of the reasons why we typically don't want to calculate this partition function. So the other quantities which we also discussed last time, let me remind you of that. So one is the so-called marginal probability. And at the end, this is a quantity we are interested in, because we are not interested in a quantity which depends on the hidden variables, or as you will see later today, the so-called latent variables. So what we want is a probability which depends on x with some parameters theta. And in the optimization, we get the optimal parameters theta. And this quantity here is just the sum, if this is a discrete set of variables, of p, of x, of hj, of theta. So that's the marginal probability. And then we have a similar marginal probability for h, which is just given in case we have discrete variables. Like this. And finally, we had another probability which we need to deal with, and that is the so-called conditional probability. And that conditional probability says that p of x given h, and I'm still having this notational clutter with the theta. So this depends also on this variable theta, but the vertical bar here means that probability of x given a specific value for h. So theta is not given a specific, that is already implicit here. And that is given by p. So this is the joint probability of x, of h, of a given theta. And this is a probability model, which we discussed before. And this is divided with h. That is the marginal probability for h as a function of these parameters theta. And then we have a similar one for h. So where h is now given by x, it's a function of theta, and it's again given by px of h of theta divided by p of x of theta. And these probabilities are the ones which are used, for instance, when we train a Boltzmann machine. And the nice thing with a Boltzmann machine is that we, depending on the type of function we have for this variable here, this f, depending on the type of function, we can get simple analytical expressions. If we have a binary so-called Boltzmann machine, we saw last time that we could get nice analytical expressions for all these quantities here. And they were given in terms of sigmoid-like functions, all of them. So I'm just reminding you of some of the things which we did last time. But then today, we are going to use Bayes' theorem. And as I mentioned in the beginning of the semester, and in other occasions, Bayes' theorem is the same as for statisticians as Pythagoras is in geometry, except that Pythagoras is something which is 2,400 years old. whereas Bayes lived in 1700, I think, something like that. So it's a much more modern theorem, you might say. So Bayes' theorem says that I can actually rewrite this quantity, this conditional probability, in terms of the joint probability, and I can rewrite that one in terms of another joint conditional probability. So let me just put that one, x as a function of theta, multiplied with p of x as a function of theta. And later I'm just going to drop this variable theta, and this has a sum over x of I if this is a discrete set of events. And this is given by h, and then I have x equal to one of these stochastic events as a function of theta, multiplied with p of x of I. And this p of x of I is also a function of theta. So pretty soon now I'm going to drop theta, because that gives a lot of, how to say, notational clutter. And it's implicit then that there is a dependence on theta in all these probability distributions. So this quantity which you see here is called a likelihood. This quantity you see here is called a prior in the literature, and this is called the posterior probability. So one of the things which I mentioned last time is that Bayesian statistics is something which really took off when people combined that with the Monte Carlo Markov chain sampling and Gibbs sampling, for instance, or Metropolis sampling and later Langevin sampling. Because if you don't have nice analytical expressions for the probabilities, or if these probability distributions are highly complicated multidimensional functions, it's very difficult to sample from them. However, you see immediately now that if this prior probability is given by a uniform distribution, and this likelihood which you have here is a Gaussian, a uniform distribution just multiplies a Gaussian with a constant. The quantity you have in the denominator here is just a normalization factor. So when you add that one, you normalize the posterior probability. So that means that the denominator is just a constant. You have a uniform distribution which multiplies with a Gaussian, which means that the posterior probability has to be a Gaussian. That's pretty obvious. So you can see, these are some of these cases of things which you can just work out immediately without thinking. Now, Bayesian statistics is extremely popular and extremely powerful, because when you train a probability distribution, you have the possibility to give an estimate on the errors which you make. You can estimate the error in the parameters theta, but you can also estimate the standard deviation, for instance, in the variable x or h. And these are quantities which we often want to deal with. Now, we are going to use this repeatedly to actually set up the algorithm for a variational autoencoder. And when we split it up, we are going to have one part which we can interpret as an encoder, and one part of Bayes' theorem here applied to variational autoencoders, which we can interpret as a kind of loosely named type of decoder. But the whole thing which you see here is based on you making an assumption about the probability. And in statistics, there's often been almost, I'd say, childish fights between a community which deals with Bayesian statistics and one which follows more the standard machine learning approach, which is called a frequentist approach, where you try to infer a probability distribution from the frequency of data. So in a certain sense, there is a strong belief in what you have here. And we will see that in order to make a variational autoencoder useful, we have to be able to simulate some of these distributions and to calculate the gradients. Because at the end, we have to calculate gradients in order to find the optimal parameters theta. Because basically what we end up doing is, if we go a little bit back here, everything we end up doing when we look at this probability here, which we assume to determine independent and identical distributed events, is that the total probability is going to be a product of all these single probabilities. And then we are going to find the maximum probability. So we're going to maximize the probability with respect to the parameters theta. That is something which we do irrespective of generative model. So we have a probability distribution and a model for that. And then we have different methods to extract this probability distribution. And then at the bottom, at the end, what we end up doing is to have a optimization problem where we maximize the probability. So let me quickly remind you of that, because that's the essence of essentially all these generative methods. So I just wanted to remind you of some of these things. So if you remember back from Boltzmann machines last week, what we did then was that we wanted to optimize. So now we were looking at the total probability X as a function of theta. And this is given by this ugly normalization constant, the partition function. And it's given by the product of all the individual probabilities, where this X of I is element of a domain of events. So this uppercase X is now all the possible types of events we can have. And this is now multiplied with this function X of I as a function of theta. And when we add this variable H, which today we are going to switch from hidden variables to latent variables, this is now given by the product X of I. I'm just writing it like this. And there is a sum over H of J. And this is given now by F of X of I, H of J as a function of theta. And the optimization problem is actually to take either the maximization or the log of this product. So at the end, the optimal theta is then given by argmax. And we have a set of these parameters, P. We assume them to be real. And then we have this log of P of X of theta. So that's the quantity which we want. And in the optimization process, what we are doing then is simply to take theta of log, and then we have P of X theta, and we want that one to be equal to 0. So just let me quickly remind you of the function which we ended up with last week. So the basic equation, which you will see again and again, and which we will play around with, also with variational autoencoders, is the following equation. So this is just a repetition from last week. So this equation here, that is the same as us taking delta, and then we have the sum over xi, and then we have log of f of x of I of theta minus, and then we had the expectation value of this quantity here, which was log of f of x of I. Now let me just write this out more carefully. So this quantity here was the same as the sum over x of I, and then I had a p of x of I as a function of theta, and multiplied with d, the derivative of log f x of I of theta. That was that last quantity. And this is something which we would typically simulate by a Monte Carlo Markov chain. Now, in our case, this function f of x of I of h of j as a function of theta is something which we define to be minus. And then we had, this is a binary Boltzmann machine. And it's called a restricted Boltzmann machine. And then we have this A of I. These are the A's are the so-called biases. And we would sum this up to a given number of nodes. These are the input nodes or the visible nodes. And then we had plus and sum over the hidden nodes up to n. and then we had a bias parameter, h of j, and finally we had this cross term over the inter layer term, where we sum over both I and j, and we have x of I, wij, h of j. So this is just one of the many possibilities which we have. And we could rewrite that in a more compact way in terms of a vector matrix notation. So we could rewrite this one as a minus, and then a of t of x plus b of t of h plus x of t of w times h. And this is a quantity we then want to optimize, because our probability, just to remind you of that one, is x of h. And now I'm just skipping this subscripts. So that is given by e of a of t x plus b of t of h plus x, and divided by the partition function. And with that, we could actually find the distribution, the marginal distribution for a Boltzmann machine. So if we then put in these different variables, this was equal to E of A of A transpose times X, and multiplied with J equal 1. So this is something which we went through last time. And we have 1 plus E of Bj plus X transpose multiplied with the correct matrix elements. And then we have a subscript J here. And we had a similar one for H. So I'm just listing them because these also define the conditional probabilities. So this was given by 1 over z of theta, and then I have E of B of t of multiplied with H. And then I had a product over I equals 1 up to the number of visible nodes of 1 plus E of AI plus WI. And now it's transposed and multiplied with a vector H. So these are all quantities which we can calculate. And one of the things which we looked at then for the binary Boltzmann machine. So we have actually the expressions, and at the end, the quantity which we want to take the derivative of with respect to theta is actually this quantity here. However, when we are setting up the network, the network, every node produces an output 0, 1, and these outputs are then given by the conditional probability. So we need the conditional probabilities for these Boltzmann machines. So what we found then last time is that this P, H of J, so this is basically a repetition of what we did last time. And now I'm skipping this variable theta, just for simplicity. And we found that that one was given by a famous function, which was just a sigmoid, E of minus, and then I have a Bj plus all the x's multiplied with the right matrix elements, and then we with a subscript j, so we have a column j. And in case we have P of h j equals 0, given x, so this takes care of all the x values. This is simply 1 minus P of hj equal 1, given x. And similarly, what we found last time is that the P of x of I is also given by a distribution which is pretty similar. It's again a sigmoid. So it makes life very simple when we're going to encode this. A of I plus Wi transpose multiplied with h. And similarly, P of x of I equal 0 is just this previous function, but where we subtracted from 1. So this should be h here, sorry. So these are all the ingredients which we need to set up the network. So you would typically initialize these x's with some random values, either 0, 1. Then you would feed them into the network, and then you get new values for h, and then you get new values for x, and then you go back and forth like that. So there is no back propagation here. You just start with an initial value for the axis, the initial configuration, and you use these values to find the optimal parameters, A, B, and W. And with those parameters, you have trained a probability distribution. And what you need in the training, so when you're setting up the network, what you need in the training then is simply you to calculate these quantities which you see here. This is done by Markov chain Monte Carlo. And this other quantity here is simply something which we can sample through because we know these different values of x's. So you would simply set up a set of initial values, and then you would calculate this quantity and these quantities as well. And all these quantities here are easy to calculate because one thing which you see is that this F, when you have a Boltzmann machine, this F is just given by x of I, h of I, j of theta is normally just given by E. And then we have this function which we defined here. This actually it's given by the exponential. And then we have one of these energy models which we plugged in here, x of I, h of I, h of j, and theta. Where this E is now, as you can see here, this E is simply given by what we have here. And it makes life much easier because then you take the log, this exponential, and then you're simply left with this function here. So that means that calculating the derivative with respect to A or B or W is pretty simple. So you have nice analytical expressions for all the derivatives, and you have nice analytical expressions for all the conditional probabilities and the marginal probabilities. And that's what made these Boltzmann machines very, I would say, popular, because you have easy and simple analytical expressions. But what you end up with is something which is less flexible, because as soon as you want to have a little bit more complicated function, that means something which is a little bit more complicated from this, it's not given that you may get nice analytical expressions. Any questions so far? So the thing which we mentioned last time is that instead of using a function like this one, you can actually replace that function with a network. And in one of the references which we gave last week, there's a reference from 2020. Actually, the last revised version was in the middle of COVID. So, and this is just something which is called implicit learning with the energy-based models. And there you would simply replace the energy function, or the energy-based model, with a neural network or convolutional neural network. So one of the things which I quickly wanted to mention is one of the examples which we have in the, so let me just bring back the Jupyter notebook here so we can go through that. So here's an example where I implement these expressions and I apply this to the MNIST data set. So my boring example throughout the lecture is just the MNIST data. And clearly, if you want to use other data sets, feel free to do that. And in this specific function, you will see now that in the RBM module, I have the conditional probabilities V to H, and then H to V. So these are the functions which I gave you the expressions of. And these are the conditional probabilities which we need in order for the nodes to fire and give 0 and 1. And it's actually pretty, it just follows up. I can actually run PyTorch here. So take a look at these codes if you want to. I'm just going to let it run in the background here, and then we come back. So this is just loading the MNIST data. Now, there is an example for energy-based models, which is something you can look up in the from the textbook by Foster. Actually, that code is a code which I think is taken from, so this is taken from another repository by a guy called Philip Lippe. And this implements a convolutional neural network as the energy-based model. So instead of you having a standard Boltzmann machine with either binary or Gaussian binary, as we discussed last time, we are now replacing that one with a convolutional neural network. This is actually a pretty good post online. And if you wish to use these models for, let's say, the second project, feel free to do that. And it's worthwhile taking a look at it. I won't go into all these details here, because the basic machinery is something which we have exposed already here in the lecture notes. And you can see now the typical reproduction of the numbers which this Boltzmann machine is doing for me. So the training loss is actually not that bad. And you can see now the numbers which it's trying to reproduce. And so this is numbers which are now generated by the trained probabilities with a binary model. And you see now that basically all numbers are numbers which you can guess what they are. At least I can. So the article which I also mentioned, which details the usage of a convolutional neural network, is actually this article here by Du and Modach here. So Langevin sampling is another way to perform this sampling. And what you typically do then when you look at some variable, so suppose now that you're just looking at a probability which depends on this variable theta, and this is the quantity you want to update. So a Langevin update of the parameter means that you take the log of the probability distribution, you have some learning rate here, which is a parameter, and then you add a stochastic term, which gives some kind of noise. So that's essentially the way you would simulate the Langevin equation. So I'm not going to set up the Langevin equation. That's a long discussions from statistical physics and transport theory. But the equation which is typically simulated one is the one which you find here. And there are actually nice examples if you wish to read more about Langevin sampling. There is a nice blog here which contains a very instructive PyTorch example on how you implement this Langevin sampling. So everything is based on, so it's actually called stochastic gradient Langevin dynamics. So what you're doing here is actually a stochastic gradient. You split it into batches and epochs as before. So there's nothing different from that. You can do this with and without momentum. You can add other methods to update the gradients. And instead of having just a fixed learning rate, you can have something which is updated with an algorithm like root mean square propagation or ADAM or other algorithms. But then the optimization is done by you having the log of the probability as the quantity you update. And this goes back to these equations which we had on the whiteboard. So if I just remind you of what we had, so let me just bring back that one back. So the motivation for that type of derivative is simply this equation which you see here. So this is what defines your gradient. And this is the quantity you then will be optimizing for the parameters theta. So instead of calculating and performing Gibbs sampling, which is the common way of doing this, you update the parameter by a stochastic gradient approach. But where now you are having this quantity as your gradients. In the previous case, which I mentioned with Gibbs sampling. So Gibbs sampling, I just want you to keep that distinction. So Gibbs sampling, as it's used in a standard Boltzmann machine, does not use gradient descent. It uses actually, you are proposing a move, and in that proposed move, you update the expectation value, and you repeat that many times. And every move is accepted or rejected with a given probability. If you do metropolis sampling, which many of you are familiar with, you obviously accept it if you go to higher probability. And then you accept or reject a lower probability with a specific recipe, like the Metropolis algorithm. When you do Gibbs sampling, you calculate the conditional probability. So you're not, in a way, when you set up a standard Boltzmann machine, there is no gradient descent in there. So the difference now, when you're looking at these more general energy-based models, is that you actually do a gradient descent in order to calculate these derivatives. Actually here, there is something which is missing here. I saw that immediately here. So that should be the expectation value of the derivative. Sorry, I was missing. Okay. So that was a kind of spool back to what we did last time. And that code example, which you see, implements a simple Boltzmann machine. And then you have these other code examples which implement energy-based models, where the energy-based model is now replaced by a standard convolution neural network. So what I wanted to do now is to move slightly over to variational autoencoders. So all this machinery here and all this kind of repetition was actually meant to remind you of some of the basic statistical quantities which enter the theory for variational autoencoders. So let me quickly remind you of the autoencoder itself, because what we end up doing is not going to look like an autoencoder. So let me just quickly remind you of that. So the autoencoder has one part where we encode the information, and that is given by a function h, and you can think of that as a kind of hidden function. So if you look at the schematic image here, you encode it. So there's this function h now, which transforms your data, and you would typically call this as a latent feature. And you can think, and this is why I'm going to keep this labeling H, even it's called a latent feature. So in the Boltzmann machine, these are the hidden layers. In a neural network, these are the hidden layers. So you could think of this as some kind of hidden degrees of freedom, which we have, which we use now to reduce the dimensionality. You remember now when we discussed autoencoders before the Easter break, an autoencoder is efficiently, if you take a simple linear approximation here, that can be linked with the theory for principal component analysis, which is a way to reduce the dimensionality of the problem. So an autoencoder itself is actually a way to reduce the dimensionality of the system. And in this case, an autoencoder could be a neural network, and the same with the decoder. So what you have then is a function where you now encode the information, and this serves as a kind of dimensionality reduction. And then the information which you have here, this h, serves then as an input to a new function g, and you have new weights and parameters to train, and that produces an output. And the metric which is used in a autoencoder is actually the difference, to minimize the difference between the input variable x which you have and this output from the decoder x tilde. And that is typically done either by the mean squared error, so where you simply take the input x minus the output x tilde from the decoder, where you have reduced the dimensionality, and then you're simply comparing these two quantities, and you're driving the optimization of w and v so that this difference becomes as small as possible. This is the similar thing which you end up doing when you do a principal component analysis. And the basic mathematics here is simply to have some function which represents this variable h, and then some function then which represents this h. And this is normally given by the different types of neural networks. And the metric is not, as I said, is either the mean squared error, or you can use the binary cross entropy if you're dealing with a classification problem. These are the two most common types of metrics in order to assess whether your model is doing well or not. So autoencoders is also something, if you are looking at project number 2, which you could use for the type of problems you're interested in. I know that many did not have time to implement autoencoders. Now, when we move to variational autoencoders, this is actually something which is different. So it doesn't have that kind of structure which you see here. And you may ask yourself, why is it called an autoencoder? In order to do that, we need to introduce a quantity or a mathematical measure of how good a probability distribution is. And there is something which is called the Kullback-Leibler divergence. So we need to introduce that quantity. And after the break, we're going to play around with this quantity and use Bayes' theorem to find a recipe so that we can actually find the final desired probability. So after the break, we are going to introduce this Kullback-Leibler divergence, which is a measure of the quality of a probability distribution with respect to what could be the true one. And it's a very useful measure. And this is the one which we manipulate in order to find an optimal representation for a probability distribution. So what I want to do after the break is more to go through the basic mathematics of a variational autoencoder. And when you see the basic mathematics, you see also the pros of the model, but you see also the limits of it. And it's going to rely on you being able to calculate gradients with nice analytical expressions, which often means that you have likelihood distributions and prior functions, which often simpler mathematical functions like a Gaussian. Okay, so the topic now is to try to outline the basic mathematics for a variational autoencoder and what kind of ingredients enter the calculations. Now, the thing which we are looking after is essentially just a permutation or perturbation of what we did previously. So we have a probability distribution, which is the marginal distribution which we want to find. And for the Boltzmann machine, just to remind you of that, we had some hidden layers, the DH here. So we integrate them away or we sum them away, and then we have the final probability. And then we take the derivative of this quantity here with respect to the parameter theta, and we want to optimize that probability. That's essentially what we did with the Boltzmann machine. And then selecting a specific form for the function gave us a recipe which allowed us to perform the calculations. Now we want to find a new recipe, which also will allow us to perform calculations. So everything with generative methods, and I'm just repeating some of the things I said before the break, deals with you dealing with these kind of approximations to the probability distribution in one or the other way. So the quantity we then want to find is this probability distribution, and we want to use the conditional probability. So this is the quantity which we end up with here, and there should be a parenthesis here. And this function, which you see the first one, this is now the conditional probability, and we call that the likelihood. And this is then the prior. And what we are going to do now is simply to try to set up ways by which we can use this equation here to find the optimal probability. As an intermediate step, we need this divergence, which we call the Kullback-Leibler divergence. So let's just bring that one up through the whiteboard here. So as I said, before we proceed, we need a technicality, and this technicality is called the Kullback-Leibler divergence. And I'm going to define this as a K of L. And it's often written in this way here. It's a ratio between two probabilities, and it's actually defined as a probability of, or that we have an integration from minus infinity to plus infinity of the domain over x. We have a probability P of x, which could be, let's say, the probability of our system. Suppose our system is governed by a Gaussian probability. And then we make a model for this probability, which we just call Q of x. So think of this as this could be the PDF, the probability distribution function, which governs our data. And then this quantity Q of x is an approximation to P. And if you have the discrete case, just let me put up that one for the sake of completeness. So the discrete case is then written in this much the same way here. And that's a sum over all the x's. And then I have P of x, and then log of P of x divided by Q of x. Now, what you see now is that if Q of x is equal to P of x, then this Kullback-Leibler divergence is just equal to 1, because log of 1 is 0. So in case we have the exact probability, then this divergence is exactly equal to 0. And whenever this P of x is 0, so let me just remind you of that. So if P of x is equal to Q of x, then this divergence, KL P of Q, is equal to 0. Also keep in mind that whenever this quantity P of x is 0, what we have then is that we know that when lim of x goes to 0 from positive values of x, log of x, that is equal to 0. So that limit, I assume that is the limit, that limit is known here. So this divergence here is what the quantity which we are going to use now, together with Bayes' theorem. So we are going to rewrite this equation so that we can actually perform computations and find the Holy Grail, which is actually this distribution P of x. So it's an asymmetric quantity, because if you interchange them, it's not a symmetric quantity, but it's used widely as a kind of measure for whether you have a probability distribution which is close to the result you want. Okay? So you will often encounter this just as a measure of the quality of a model which you make as a probability distribution. So you're assuming here that you have a P of x. This P of x could be just a probability distribution which you have made up. And then you're trying to find another Q of x which resembles that probability distribution. Okay, so the question now is, how do we use this for, say, Boltzmann machines or variational autoencoders? So how do we use for a variational autoencoder? Or we could also think of this in terms of the Boltzmann distributions. There is nothing which hinders you actually using this Kullback-Leibler divergence for any of these generative models. So what we are going to do now is to say that we have a marginal distribution. So we have, so let me just introduce then, have our marginal distribution. And this marginal distribution is something which I'm going to call here for Q of X. And this is actually the origin. So I'm just going to make some kind of shorthands here. And then so if you now look at, so this Q of X, which you saw here, which you see in this equation, is something which I'm going to identify with the probability we are aiming at. So this is what we want. Then we may have some data. So what I'm going to do now is then in the equation above, so we're going in the above equation, in the KL divergence, that means this expression which I put up here, in the KL divergence, and this is just notations which I'm bringing up here, I'm going to let this P of X represent our data. And then I'm just bringing in another function which I call f of x, just to avoid some confusion, because we've been using this one for the marginal probability which we want to find. So now I'm assuming that there is some probability distribution which represents our data. So that means the following. It means that this, if I take this KL quantity, so I have f of x, which now is a probability distribution which represents the data. I don't know this function. And then originally what I want is this P of x of data. So this is what I want. And I'm going to replace that with our Q of x later, but I'm just going to keep this P of x here. So that means that what I get then is the following. Minus infinity to plus infinity. I have this f of x, and then log f of x, and then I have P of x of theta. And then I can obviously rewrite this one in terms of minus infinity, and then I have f of x of log f of x of d of x minus, and then I have f of x of log of P of x as a function of theta of d of x. Okay. So the only thing I did now was just to rewrite these quantities, and then I recognize these quantities as expectation values. So the first term is just the expectation value of this quantity x, which follows f of x. So this is a more compact notation, which is quite common in the literature. And we are taking the expectation value of log f of x. That's the first quantity. And this is taken with respect to the data which we have. And this is minus, and then I have e, and x follows this f of x. And then I have log of P of x. So these are just expectation values. So when we optimize with respect to theta, the first term is actually independent of theta. So when we are performing the optimization, so just keep in mind now that this term which you see here, this one is independent of theta. Because that's a true distribution. And there is no point in having a parameter theta for the true distribution. So that means that when I take the derivative with respect to theta, that first term is equal to 0. So when we are performing the optimization now, it's actually the second term here, which becomes a little bit more interesting for us. So just keep in mind then that if we just continue along these lines, so that means that the derivative, so when we optimize, this term does not contribute. This term is actually 0. It vanishes. So what do we want in a VAE, in a variational autoencoder? So we want this quantity here, and we want that one to resemble the true probability distribution as much as possible. And we can now rewrite that in terms of the likelihood there, the conditional probability, times P of H of D of H. And then we use maximum likelihood to find the optimal probability. And then we use max likelihood to find, as before, the optimal parameter theta. So in the variational autoencoders, what is pretty common, let me just mention that for you. In a VAE, what is common is to assume that this Px of H is a Gaussian. So this is then given by some normal distribution of X with a mean value, which I'm just going to call A G of H of theta. So that's the mean value. And then it has some variance, sigma squared, and often it's made diagonal. So that means that the covariance contains only diagonal elements. And you will often see that one just multiplied with the identity matrix. That is one of the most common approaches, which is being used. So one of the reasons for that, because if we do this, we can use gradient descent. And the output which we have is not required to be a Gaussian. The important part is that this P of X can be, this P of X, the conditional probability, this X given H can be computed, and that we can compute the gradients without too much difficulties. So the output does not need to be a Gaussian. Output not necessarily a Gaussian. But what we want to have is a kind of recipe which allows us to actually perform calculations. And when, as you will see a little bit later, if we have Gaussians, it's actually easier to calculate the gradients because you get nice analytical formulas for the gradients. So when we want to solve these equations for P, so to solve for P of X with a given theta, we must deal with the following problems. So I'm just writing some text now. Deal with one, how to define the latent variables, or you can call them the hidden variables. Which we call H. And then how to integrate. Or we should rather say sum here. So these are the two problems, two of the problems which we need to define before we actually get started. So it's conceptually simple to just compute this probability by sampling a large set of these values H. And that means that your probability would simply be the sample over this large set of variables. So this is a pretty straightforward. However, the problem then is that what you face is that if you have typically a multidimensional probability, you will need a huge space to sample over. So a straight or direct approach that is sample over large space, a large set of this H. So you could have a set of values here, which go from H1, H2 up to Hn. And then you would simply compute the following quantity. So P of X of theta is then simply proportional to 1 over n. And then you would have a sum of I equal 1 up to n. And then you calculate this P of X of H of I with a parameter theta. So this is to obtain this quantity which you have here. But then after you've done that, you will take the derivative with respect to theta. So because if you look at the equation which you have here, this equation here, if you assume what is typically done is that H is given by a uniform distribution. So if you assume that, then it's pretty straightforward to calculate this quantity. And you need to have a model, obviously, for this quantity to be able to do that. Now, if you look at this straightforward approach, the problem you face then is that you would need a huge space if your function is a high-dimensional one. And clearly, if it's a high-dimensional one, you can actually run on for an infinite amount of time. So the problem which we also face is that for most values of H, this function which we have here can be nearly zero. So suppose you have a probability distribution which covers a wide domain. You can still risk when you pick these variables H randomly that you may actually have function values where this contribution P of X given H here is close to zero, always zero. So that means that you would be wasting a lot of cycles. So this recipe, it sounds intuitively simple, but it's not very practical because in general, the probability distribution which we want, this P of X, is normally a high dimensional probability distribution. So this recipe sounds intuitive and simple to implement, but it's not very useful. And this is also one of the reasons why people don't use it. So the key idea behind these variational autoencoders is to attempt to sample values of H that are likely to have produced X, and then you would compute this P of X as a function of theta just from those values. So what we are going to do now is introduce a new function. So we need a new function. We introduce a new function. So keep in mind that what we were doing here was actually to take, we were looking at P of X, and now I'm skipping theta. So this was a quantity we looked at. So, but we are now going to introduce a new function, which is the other conditional probability, which is given by H as a function of X. And that function can take, so let me explain a little bit why I introduced this function. It can take a value of X and give us a distribution over H values that are likely to produce X. So I'm going the other way around. So I'm actually finding a function which can take a given value of X. So X is actually the domain of events which we want to reproduce. So just keep in mind that X is now a set of variables which we are training the probability against. So you may have positions of particles, And then you want to find a probability distribution which reproduces that position of particles. So X is in a certain sense a known quantity from the data which we use to train a probability distribution. So what we are doing now is that we want to find this function, and then we have the probability of finding H given X. And then we can turn around and then find a model for the probability X given H. And then with that one, we want to generate this quantity here. So the hope is that the space of these values of H is smaller than the space of all the H that are likely under the previous prior P of H. So what we want to compute then, so hopefully, let me write this down as well. Hopefully, the space of H values under this quantity Q is much smaller than the space of all these H values that are likely to belong to the prior P of H. So if you look back at the equation which we had here, the equation here, what we have is a prior here, and that can actually represent a huge space. So what we want to do now is actually to limit that space through some kind of likelihood here, so that the total number of H values which enter the calculation of this integral is not that big. See the basic philosophy here? So what we are going to compute then, so we are going to need a quantity which we want the expectation value of this H which follows this distribution Q for this quantity X given H. And we want to compute that one relatively easily. So we have a distribution of values H which follows this, or this values H which follows this distribution Q, and we want to compute this quantity here because that's the one which enters the calculation of the final probability distribution. So the relation between this quantity which you see here, so the relation between this one and this quantity P of X of theta, that is actually one of the cornerstones of Bayesian statistics. So this relation is one of the cornerstones of Bayesian statistics. So what we're going to do now is actually to bring back, to see how we can use this, we bring now back the Kullback-Leibler divergence, KL divergence. And the Kullback-Leibler divergence in this specific case is something which we are going to define in terms of this probability Q of H with respect to this probability of H of X. So we are now looking after this probability here, but we want to use that one to model this quantity here. And QH is an arbitrary function of H and may not depend on X. So this is an arbitrary function it's called the prior of H, and may not depend. Actually, normally, it's seldom you allow that kind of dependence, and may not depend on X. So if I now use this Kullback-Leibler divergence, what this is going to be now is going to be equal, this quantity, if we now go on to the other slide, this will simply be given now by the expectation value of H using sample from this distribution Q of this log of Q of H minus log of P of H of X. So remember that this is actually the same as an integral over D of H. And then I have my quantity Q of H of log Q of H minus, and then I have D of H of Q of H of log of this quantity P of H of X. So this kind of compact notation, which you see here, is nothing but just us writing out the Kullback-Leibler divergence in terms of these expectation values. So we can then get P of X into this equation. So how do we get P of X and P of X of H into this equation? Because these are the quantities we are interested in. So just keep in mind that what we are doing now, we are in a way going back to the problem which I mentioned here. So we want to define the latent variables, how to integrate over H. We don't want to take this direct approach here. The original equation which we want is actually this one. And in what I showed you now, this doesn't appear, this doesn't appear. I have, however, a model for the prior, which I call for Q of H. However, that depends again that this Q of H can span a huge space so that many of the values of this conditional probabilities could be zero. So the question is, how do we limit the integration over these values of H? So how to integrate over the sum, and also how to define these latent variables so that we can get a recipe which allows us to sample quickly and in a meaningful way. So the thing now is that we are going to circumvent the problem. And then, as I said here, how do we get that one? So the way we get that one is actually to apply Bayes' theorem. So we are circumventing the problem by bringing back, apply Bayes' theorem. And this is normally what is done. So let us bring back Bayes' theorem. So if I do that, I can actually, so if you then look at Bayes' theorem, it means that P of X H is actually P of H X multiplied with P of X divided by P of H, so which is a normalization constant. And then vice versa, if I want the PH given X, I would then get a similar relation. So I can then bake in Bayes' theorem. So I can rewrite this quantity here of Q of H given P of H of X. So what I want now is that this divergence should be as small as possible, because then I have a decent model for this PH given X. So X is fixed. These are the data which we have as input. And now I want to use X to restrict the values of H, so that when I perform the integration, I can have the integration over variables of H which give contributions which are non-zero to the integral. even if H can be a huge space of variables. So when I now introduce Bayes' theorem, so I'm just giving you the answer here I get as a function of this Q. So H is generated by a prior. Then what I get is log of Q of H minus, and then I have log of P of X. So I'm just using Bayes' theorem. So note now I have X given H minus log of P of H. But then I have a quantity which does not depend on H. Because now if you go back to Bayes' theorem, so I'm simply plugging this quantity into the equations which you see here. That's the only thing I'm doing. And then there is a quantity P of X here, which does not depend on H. So I can take that out from the expectation value, and that gives me simply plus log of P of X. Now keep in mind that I have taken out theta dependence. So this quantity which you see here, this quantity has actually a dependence on theta. Because this quantity here is actually the optimal probability which I want at the end. It's this quantity which you see here. So I've taken away the theta dependence simply just to avoid clutter in the equations. But this quantity which you also see here does not depend on H because we have integrated away H. And this is the quantity which we want. So if you look at this Kullback-Leibler divergence, we can now just rewrite it and simply just rewrite this equation. So I shuffle over some terms. So I'm going to define a left-hand side and a right-hand side. And then I'm going to reuse the Kullback-Leibler divergence because two of the terms here, like these two terms here, can actually be rewritten in terms of the Kullback-Leibler divergence. So what I'm going to get then is the following equation. So I can rewrite this in terms of the Kullback-Leibler divergence of Q of H. And then I have P of H given X. And this is equal to the expectation value of H given this distribution Q. And then I have my log of P of X of H minus the divergence here for Q of H and this P of H. So keep in mind that X is fixed. This is fixed by all input data. And this Q can be any distribution. And since we are interested in inferring P of X, it makes actually sense to actually contrast this variable of Q so that it depends on X. And in particular, what we want now is to have the quantity which you see here, this quantity, as small as possible. So when I'm performing the optimization now, there is actually a point here which is a little bit more delicate. So when I optimize my probabilities, because at the end, we are going to take a delta of theta here. That means that when you look at these terms here, these are terms which I can calculate and just deal with a gradient descent method. So I can calculate these terms here. And I need to make a model for this Px of H and also for this Q of H. And the point now is that if we train this one, or rather we train this one so it mimics that one, then this ratio is going to be close to 1. And that means that we can forget this term. This is normally forgotten in the actual calculations. And then we are simply left with log P of X. And then we can take the gradient of log of P of X with respect to theta. And then the quantities which we need to deal with actually the quantities which you see here. So let me add some more statements here, which I have collected and which you will also find in the lecture notes as well in the slides. So the left-hand side of this quantity is a quantity we want to maximize. So this is this quantity here. And log P of X plus this arrow term. You can think of this as an arrow term. And these are the quantities which we now want to maximize. And we can now maximize it so that this probability Q of H can reproduce a given X, as you see here. Now, the right-hand side is something which we can optimize with stochastic gradient descent. So if we now single out this piece here, this is the part we will use stochastic gradient descent on. Gradient descent. And obviously with given the right choice for this quantity which you have here. So in order to calculate that one, or to be able to apply gradient descent, we need to find a function for this Q. And one of the standard approaches is actually to use a Gaussian distribution for Q. And that's going to give us gradient expressions, which are going to be analytical in terms of gradient of Gaussians. And that is going to simplify the calculation of a stochastic gradient descent approach. So the equation which you see here, and this is where the naming and coding comes in. So if you look at the right-hand side, it has a form which kind of looks like an autoencoder. So the term Q is encoding X, and then into this variable H. And this term which we have here, the term P here, is actually decoding it in order to reconstruct X. So you can think of this term here as a kind of decoder, and this term which you see here as a kind of encoder. So we are encoding this term here, we find all the relevant values of H, and then we decode it so that we can actually extract the most relevant values of the probability P of X here, which then can be used to calculate the final probability P of X. So I see my time is running out here. I'm going to repeat some of these things next week. I was hoping to get to GANs as well, but we will deal with that next week. So next week, I'm going to wrap up this discussion. And then we are going to look at how we can program a variational autoencoder. And we are going to look at results. I mean, there are tons of programs online. If you go to the Jupyter Notebook, so let's just take a quick look at that. So the everything which you see here is actually a repetition partly of what I put on the slides. So, and these are the equations which we actually end up with. And at the end here, so if you now look at, so we're going to complete that one. We're also going to look at some of these coding examples. So this is an example which is taken from this link. It's actually from Keras. And there is also an additional code here, which we're going to discuss in PyTorch, and how you can include and encode the variational autoencoders. And we're going to wrap up the discussions because I need at least another 15-20 minutes to wrap up the mathematics for an autoencoder. And with that, we can look at the codes, and you can decide whether this is something you want to explore as part of the second project. And after that, we are going to look in general adversarial neural networks. And finally, we're going to jump into diffusion. So I didn't finish in time what I wanted to say about the variational autoencoders, but this is something which we will pick up next time and then try to wrap it up. I'm also going to send you, there are several tutorials on variational autoencoders, which you will find useful to read as well.